Good morning and Assalamu alaikum. Now I will be talking about the analysis of the robotic manipulator that was able to conduct the MATLAB. So as you can see in our MATLAB, we perform two kind of analysis. Perform the forward kinematics and the reverse kinematics of a robotic manipulator. In the first two course, I will be talking about the forward kinematics, and the second two course, I will be talking about the reverse kinematics. So first I did, I planned to plot a graph of of the position of each of the position of the end effector with respect to each axis with relation to time. To do so, I first was able to demonstrate the variable time between 0 to 1 second with a spacing of 0.01 seconds. Furthermore, I was able to relate Q2 and Q3 and T1 as a function of time. And as you can see, I was able to perform the analysis and I was able to perform the analysis and I jotted down in the report and I was able to equate the version of at the end factor with respect to each axis x, y, and z, and I was able to relate with each of the joint parameters. These are the equations which relate the joint parameters with the end effector's position. With this, you can see we were able to plot the graph of t with respect to t with respect to the position of the end factor in x-axis, in y-axis, and z-axis. I'm going to comment out these two, and I'm going to plot the graph of t with respect to the position of x-axis. Now I'm going to repeat the same procedure, but this time I'm going to comment out this code. I'm going to repeat the same procedure, but this time I'm going to do so for position of end factor with respect to the z-axis. Okay, so as you can see, these graphs have been provided in the report. You can see the graphs from there. Furthermore, if you want to review the graphs again, you can pause the video. Now, as you can see, the analysis that I performed in this code was conducted by my own analysis. Okay, but this time I'm going to be incorporating the Peter Cook robotic toolbox. And I will be using that particular toolbox to perform the analysis and to ensure that my initial analysis was to ensure that my initial analysis matches the result right now. So in this code, I will be incorporating the Peter Corp robotic toolbox. So here, as you can see, I defined the DS table of my robotic manipulator. I've defined the DS table of my robotic manipulator where 0 0.5, 0 0.6, these variables, that is, this value as you see, defines the length line of D1 and A1 as well. I jotted down and I was able to plot the robotic plot. I'm going to run this code. I'm going to run this code, and as you can see, this is as you can see, this is the diagram of the robotic manipulator, and it matches with the diagram that we have shown in the initial report. Okay, so now I will be using, so basically in the Manipulator called robotics toolbar, you can perform various functions. You can perform the robotic forward kinematics, inverse kinematics. Furthermore, you can plot trajectories, and you can also simulate your robotic manipulator. So in order to perform the forward kinematics of a robotic manipulator, we will be using this function robot.fkind. Okay, and after using this function, we are going to define the joint parameters in the function. This function will allow us to, so after adding the joint parameters at the input of the function, we will be able to get the translation matrix of the end effector. And using the transformation matrix, we will be able to find out the position of the end effector with respect to x, y, and z. As you can see right now, we have defined Q2, Q3, and T1 as a function of time. We're going to run this code. I'm going to comment out the unnecessary plots. We're going to run this code, and with this, When we run this code, and with this, we will be able to plot the function of px with respect to time. And as you can see, this graph matches with the graph that I was able to plot in initial analysis. Since the graph of both analysis match, this confirms that my initial analysis was correct, and the equation that I derived over here matches with the forward kinematics of the end effector. I'm going to perform the same analysis for the. So I'm going to comment this out. I'm going to comment this out, and as you can see, this is a question. This is the position of the end effector with respect to the y-axis against time. Similarly, I'm going to comment. Similarly, I'm going to comment out the rest of the code, and this is the position of the end effector with respect to the z-axis with respect to time. Okay, now moving onwards, now I was able to talk about the power kinematics. Now I'm going to be talking about the inverse kinematics of my derivative. What is manipulator? So basically, in the inverse kinetic, you add in the end effectors, position vectors, and you're able to find out the joint parameters of the position. And in a particular robotic manipulator, we have three joint parameters. We have T1, Q2, and Q3, right? So we will be inputting the joint end effector position, and with this, we'll be getting the end effector joint parameters T1, Q2, and Q3. So as you can see, now this is the code for our inverse kinematics. As you can see, the position of the end effector with respect to x, y, and z as a function of time. We have defined the length lengths 0.6, 0.5, 0.4. Okay, so in our initial analysis, we found out that the joint parameter d1 is equal to pz. That is simple. And in order to find out q2 and q3, we were able to find a series of functions, and the analysis that have been performed has been noted down in the report. Furthermore, the equations were added to the MATLAB to plot the appropriate graphs. So as you can see, we have two variables. We have Q2, we have Q3. We're going to perform the analysis from 0 to 1 second with a spacing of 0.01 seconds. I have commented out the two codes of D1, D2, of D1 and Q2, and after pressing the run button, you can see that this is the graph of the joint parameter Q3 with respect to time. Similarly, as you can see, this is the graph of D1 with respect to time. I believe that there's some kind of error. Let me just check it out once again. Okay, so yeah, this was an error. Let me just correct it. Yeah. So as you can see, this is the graph of D1 with respect to time. Last but not the least, so last but not the least, as you can see, this is the function of Q2 with respect to time. All of these graphs have been added into the report, the final report. So you can easily view these graphs in the final report that we have added. So now this was the analysis that we were able to perform by ourselves using the knowledge that we have. Now once again, I will be incorporating the Peter or robotic toolbox in order to confirm my inverse kinematics analysis and to ensure that my analysis, the equations that I was able to derive from inverse kinematics are actually true, are actually correct. So like before, we will define the TS table of our inverse kinematics. Sorry, let me just uncomment this here. So as you can see, this is the DS table of a robotic manipulator. And as you can see, there are four variables: 0.5, 0.6, 0.5, and 0.4. And these are the variables to define the link length or link length of the robotic manipulator. I'm going to use this code to, so yeah. So like once again, as you can see, we are able to define time between 0 to 0.1 to 1 seconds. And here, as you can see, we have the position of px, py, pz, which is as a function of time. So this is, so now as you can see, so like I said, with our inner Peter-Cock robotic toolbar, we can perform forward kinematics, and further we have a function in order to perform the inverse kinematics. Okay. So in order to perform inverse kinematics, we have to have a series of input which are jotted down as the variables. Okay. First of all, we have to tell the position of the errand factor with respect to time. This is done by done by inputting the transformation matrix of the errand factor. Furthermore, we have to define the initial angle. So basically, how the inverse kinematics is performed in the Peter-Cock library is done by a series of iterations. So in order to conduct the iteration, also have to define the initial angle where the robotic and where the joint parameters can supposedly be. In order to do so, we will also be inputting the initial angle, rad1 and rad2. And in order to find the initial angle rad1 and rad2, we were able to find out a series of functions which we were able to relate the rad1 and rad2 with respect to time. This is the initial angle, and this is the max function which is necessary in order to perform the inverse kinematics. After performing the inverse kinematics, we were able to find out the T1. The T1 we found out, and with T1 there's T1. With T1 we were able to separate out the matrix into three joint parameters T1, Q2, and Q3. So with this, we were able to perform the inverse kinematics of our robotic toolbox. Next, what are we going to do? We are going to plot a graph of time with respect to each of the joint parameters. So first, I need to comment this out. And as you can see, this is a graph of D1, the joint parameter D1 with respect to time. And as you can see, there is a bit of a distortion, essence, maybe because there might be some kind of error. Let me just check it one again. Okay, so yes, there is some kind of error. I'm going to address this. But let's go on with the other two graphs. Okay, so okay, sorry, just give me a second. Okay, so this is let me just comment this out. Let me just comment this out. So as you can see, this is the graph of time of this is the graph of the joint parameter Q3 with respect to time. And as you can see from our initial graph, this is a graph of Q3 with respect to time. Okay, so as you can see, this graph does not match exactly with the graph that we have performed in our initial analysis, and there are a number of reasons for that. Because first of all, in our Peter-Cock library, only 100 iterations are performed to come up with a solution. If more than 100, for example, up to 1,000 iterations are performed in our Peter-Cock in our inverse kinematic analysis, I feel like we will be able to get a more accurate result. As for this moment, even though the trend of the graph matches with the graph that we were performed in our initial analysis, but despite that there's some kind of error. But it is enough to prove that our analysis that we have performed before that is correct, and the equation itself satisfied. In order to furthermore confirm our analysis, we'll be also plotting the graph of Q2 with respect to time. So like I said, I'm going to comment this out. I'm going to uncomment this line of code, and then I'm going to comment this out. And after pressing the run button, we are going to be able to find the graph of Q2 with respect to time. So yes, once again, And once again, you see the same error. As you can see, the trend of the graph once again matches with our trend that we were able to perform in our initial analysis. But once again, there is also some kind of error between the two graphs. One, and I feel like this error can be reduced once more if you can perform more iterations in our inverse kinematics. Unfortunately, there are hundreds of iterations that are set at default by the Peter library, and unfortunately, we can't change the number of iterations. We can't increase the number of iterations. But despite that, this analysis proves that the inverse kinematics that we performed before that was correct. That is correct, and it matches with our analysis. So as you can see, we use the MATLAB. So as you can see, we use the MATLAB to perform the forward kinematics and inverse kinematics, and furthermore, we also use the matrix in order to ensure that our analysis is correct and is sound and is correct. Furthermore, Moise is now going to be Moise is also going to be sharing a video in which he's going to talk about the analysis of the robotic manipulator that he performed in MSc Adams. Thank you for your time. Allah Hafiz.